Hey everybody, hope you're doing well today. In this video, I'm kicking off a 4-video series that deals with center of gravity and how center of gravity affects overhead lifting, how center of gravity is related to overhead lifting. Center of gravity is often overlooked as an important variable, but it can affect the sling loading, the balance, the unintentional movement of a load if we don't pay attention to center of gravity and identify pick points and place pick points in the proper location relative to that center of gravity. Again, a 4-video series. This first video is just an overview of center of gravity, overview of rigging, very simple. Most of you have heard a lot of this before, but I just wanted to set the stage for the other 3 videos where we'll talk about methods that can be used for identifying the center of gravity of a load. It's not always straightforward. Sometimes it's easy, sometimes it takes a little bit of thinking, sometimes it takes a little bit of math, some engineering to determine the center of gravity of certain types of loads. All right, enjoy the video. Okay, let's talk about center of gravity as a concept, just in general. What do we mean by center of gravity? As I said in the introduction, this is the first in a 4-video series. We're just generally going to talk about center of gravity and suspended loads. In the second video, we're going to talk about finding the center of gravity, and we're going to look at 2 methods, the trial and error method and what I call the straight line method. Then in the third video, we're going to deal with more complex types of loads, what I call a system load, where there are a lot of different components making up that load, and you really need math to find the center of gravity for this type of load. Then in the last video, we're going to take a closer look at how the center of gravity affects sling loading, or the amount of load on our rigging and different components of our rigging. Also, I'll talk a little bit about how we determine the correct pick points for certain types of loads. Again, correct pick points relative to the load's center of gravity. Some terminology before we get started. Again, some of you have had my classes before and this is familiar to you, but if not, let's just talk about some basic terminology that I'm going to be using during this video and the other 3 videos. First of all, rigging. That's the equipment we use to connect a lifting machine to the load that's being lifted. It's the equipment that we use to connect a crane to the load that the crane's lifting. And I'll talk mostly about cranes with reference to rigging, but rigging also applies to other types of lifting equipment also. We can think of rigging another way. Anything between the crane's hook and the load itself is rigging. Pick point is a location on the load where the rigging equipment is attached to the load. Many loads will have what we call engineered pick points that are designed by an engineer and are a part of the object being lifted. That's the ideal situation. Engineered pick points that are always there. You don't have to make sure you're choosing the right device for the pick point. It's always there. It's designed according to engineer specifications, and that is the ideal situation. That's not always the case though. Sometimes we need to pick up a load where there's not a handy-dandy eye bolt or a hook or a shackle to connect to, and we have to come up with some way of making that connection. In that situation where we have to come up with our pick point, the pick point hardware or device is part of the rigging design. If it's an engineered pick point, the pick point is not considered to be part of the rigging design. Another concept that we'll talk about, especially in the 4th video, is sling loading. This is the force imposed on the rigging components. And some of you have seen this before in other classes, but something that's counterintuitive, it's not commonsensical, but the load on the slings, or the load on the rigging, can exceed the weight of the load itself. We could have a 10,000 pound load and the force imposed on the sling legs could be 12,000 pounds for each leg. Some of that's due to center of gravity. Some of it's due to sling angle. There's several variables involved in determining sling loading. Video 4 will take a closer look at sling loading and see how it relates to center of gravity. In the picture to the right, we have a pretty good rigging design. We have our rigging devices up here. We have slings and spreaders and shackles. And on this particular load, they do have engineered pick points. These are the pick points. They have 4 pick points on each side of this particular load, which is perfect. It makes it a lot easier for the rigger and the crane operator, the project manager, when they need to lift a load that has these engineered pick points. A lot of times these loads like this, they will come with instructions from the manufacturer. These instructions will tell whoever's picking up this load how they should do it. Suggestions or guidelines for how the load should be rigged for overhead lifting. This information from the manufacturer should also include the centers of gravity, where the center of gravity of this load or these loads are located, and how that relates to rigging. That doesn't always work out that well, but that's in a best case scenario, and it's not that uncommon that an object arrives at your job site, at your factory, and everything's laid out. There are all the instructions you need to follow for rigging that load and picking that load and sitting it up on top of a building or on top of a rack or wherever it's going. Okay. So moving on. Why does it matter? Center of gravity, the location of the center of gravity. Why is it important? If a load is not rigged to its center of gravity, which it should be, we'll talk more about what that means, it's going to be more difficult to handle. It's going to be more difficult to place the load at its destination. You may end up with some unintentional, unanticipated movements in the load. It may start spinning on you, especially if you're using one sling leg. If you have a single leg sling picking up the load, you're much more likely to see spinning problems. But even with multiple leg rigging designs, you could have spinning, you could have swinging, or other unwanted movements. And those unwanted movements are referred to as dynamic loading. Dynamic loading increases the stress on the rigging, increases the stress on the load, and can also increase the stress on the lifting machine, the crane or other machine using to make the lift. It can even stress the machine to the point that there can be structural failure or a tip over of the machine if that load starts swinging, if it gets out of control with these unwanted movements. But if we rig to the center of gravity, we can help avoid those types of unwanted movements. If it's not rigged to the center of gravity, there's increased stress on rigging components. The load may be damaged if it's not rigged properly. Some types of loads, a liquid load or a granular load, let's say it's a container of grain, container of wheat, and it's not rigged to its center of gravity and it sits out of level, you may end up spilling part of that load in the process of lifting it. Liquid, same thing. If it's a liquid load, if it's not level, there's a potential for spillage and loss as a result of that. Could also potentially harm someone that's in the area, depending on the type of load. If it's spilled on the person, it could cause physical harm to that person. If it's not rigged to the center of gravity, it's impossible to accurately determine the sling loading, how much of a load is on each part of your rigging system. Now, there are lifting operations where an unlevel configuration or an unlevel position may be desirable. These are rare situations, and if you do need to lift your load so that it's not level, that needs to be considered in the rigging design. And ideally there will be an engineer qualified in rigging design that's involved in this type of load where we want to purposefully rig it so it sits off level. You may also run into a situation where you pick up the load and it's in a horizontal configuration, and during the course of that lift, you have to rotate the load from a horizontal to a vertical position. Also, you really should have an engineer qualified in rigging design involved in that process to make sure that all of the components are set up properly, that you have all the different types of devices that you need. And once you have those devices, make sure that they're all configured properly. Engineers worth their money in situations like that. All right, so just a few reasons why it matters, why we need to pay attention to the center of gravity. So now let's talk about what we mean by center of gravity, also referred to as the center of mass. I'm an old guy coming up, we call it center of gravity. You talk to an engineer, they may refer to center of mass. It's in essence the same concept that we're dealing with. We can think of the center of gravity or the center of mass as a geographic point, a location on the load around which the load's weight is evenly distributed. A point around which the load's weight is evenly distributed. We can think of center of gravity in 3 dimensions. We can think about the center of gravity positioned relative to a horizontal x-axis, a horizontal y-axis, and a vertical axis, where there's a horizontal center of gravity for the load and a vertical center of gravity for the load, a vertical point around which the load and its weight is evenly distributed. We're mostly going to focus on the x and y dimensions for this series of videos, and that for me in lifting, overhead lifting operations, those are the most important dimensions. I will mention the vertical at different points throughout the series, but for the most part we're focusing on a 2-dimensional center of gravity, the x to the y axes. Another thing to consider, some other things to consider with center of gravity. Depending on the weight distribution and or the load shape, the center of gravity may not be the geographic center of the object. That's really pretty common with odd-shaped loads or loads with an uneven weight distribution. And that's what we're focusing on in the other 3 videos, or at least 2 of the other 3 videos, is finding that geographic center, or finding that center of gravity when it's not the centroid or the geographic center of the object. Another thing to consider that occurs occasionally, the center of gravity may be outside the physical bounds of the object. We run into this also with odd-shaped loads. I'll give you an example in subsequent slides of types of objects where this center of gravity is not within the physical bounds of the object itself. And I threw out a term here, centroid. There's what we mean by centroid. I just didn't want to leave that loose end in case anybody's wondering what the heck he means by centroid. The geographic center of an object without regard to weight distribution. It's the center of the object without regard to weight distribution, whereas center of gravity is based upon that even distribution around the point. And it's not necessarily going to be the centroid of the object. Here are some examples of some simple loads or simple shapes where it's really pretty easy to find the center of gravity. We have a rectangular shaped load, assuming that the weight distribution is uniform. It's going to be at the midpoints of this load. Here's our vertical center of gravity. Here's our horizontal center of gravity. A shipping container. That's a common type of load you'll see lifted in industrial settings, construction operations. Shipping containers, if the weight is evenly distributed, the center of gravity, the vertical center of gravity is here, and the horizontal center of gravity is going to be the same position at the top of the load. But one thing you run into with shipping containers, and you need to be aware of, the weight may not be distributed evenly within the shipping container. So before you're going to be picking any shipping containers, you need to open it up, you need to know what's inside the container, and get a handle on the weight distribution. You could have a 10,000 pound forklift in this end and a boxes of paper cups in the other end. This is going to be your heavy end. The center of gravity is not going to be the middle. It's going to be more toward that heavy end. And the videos 2 and 3 will talk about in these situations where there's not an evenly distributed load, how we find that center of gravity precisely. Here's an object, a ring, and there are industrial settings where large steel rings like this are used for different purposes. If you have a large steel ring that weighs 800 pounds, its center of gravity, assuming that everything is evenly distributed, everything is uniform, that center of gravity is actually going to be outside the bounds of this object. It's going to be right square in the middle of that opening. Type of load that I dealt with a lot in my career were precast concrete bridge girders. Most of the time, these are fairly simple to identify the center of gravity. If they are uniform in weight distribution, the center of gravity is going to be right in the middle of the girder. But you do run into situations where maybe there's not an even distribution of weight. The weight is unevenly distributed. Maybe you have one end that's heavier than the other end. When they manufactured the girder at the factory, it was cast so that maybe this end is thicker and heavier, or maybe this end had more steel bars in it, or there was something about one end or the other that resulted in an uneven weight distribution. If that's the case, then you need to do a little more investigation. You need to perhaps use some mathematical methods to determine what the center of gravity is for this type of load. But usually with bridge girders, it's pretty easy, pretty straightforward, especially concrete. Steel can be a little trickier. And one of my examples I'll talk about in video 2, we'll talk about steel girders with different weight distributions. Yeah, these are for the most part easy though. What we're really focusing on in this video series are odd shapes or loads with an uneven weight distribution. Maybe a triangular shape or an L shape. How do we find that center of gravity? And this is the center of gravity symbol, universally used in diagrams and when talking about center of gravity. The symbol that I'm using here and throughout the video series, that's what that is. That's indicating the point around which all of the weight of this load is evenly distributed. But how do we determine that in an L-shaped load? We'll take a look at that. How do we determine the center of gravity in a load like this? We have a rebar cage that's probably 60 feet long. The lower part of the rebar cage has a lot more steel in it than the upper part. A lot heavier down here than it is up here. How do we find the center of gravity of that? We'll talk about the methods. Another situation that you may run into as a safety professional or a crane professional, you may have to lift the upper works of one crane and set it on the crawler assembly of another crane. That's when cranes are assembled. Some types of cranes, you lift the entire upper works or this part of the crane that most of us would call the cab or the engine compartment. We have to lift this and set it on another part of the crane during assembly. During a disassembly, we go the other way. We take it off. But with a load like this is the engine compartment back here. That's the heavy end. This is the cab where the operator sits. That's the light end. When we lift this thing up, we need to, before we start lifting, we need to know where that center of gravity is, because that's going to help us determine where our pick points are going to be so that we lift this thing and keep it level, which makes it easier to position when we get to the point where we're sitting it down. This is another example of a complex, what I call a system load. We've got one video just on system loads, number 3. But this is part of an air conditioning system, an industrial air conditioning system. You have pumps, you have tanks, and they're not evenly distributed across the footprint of this object. This end for me right now, that looks like that's going to be the heavy end. But we also have, it looks like some kind of tank here. What's the weight of that tank? Then we have all of these components up above this lower level. With this type of system load, we have to use what I call the component method to precisely determine the center of gravity for this load. And all of this will be explored. All of these mysteries will be solved before we are done with this video series. Now here are some best practices. I've already alluded to these with regard to rigging to the center of gravity. Your hook should be directly above the horizontal plane center of gravity. The hook, we're talking about, well, think of the hook as being part of the crane. That hook block, that load block needs to be ideally directly above the center of gravity. And here are two examples where that was achieved. We have our center of gravity, hook directly above. Center of gravity, hook directly above. When we hoist this load, it's going to remain calm. It's not going to swing. It's not likely to spin. It's going to remain level when we have the center of gravity configured to our hook in this way. That's ideal. That's a best practice. If not, load will not be level and will be more prone to dynamic movements. Now, if we aren't rigged to the center of gravity, say with a cylinder like this that we're lifting, let's say we're a little bit off to the left or a little bit off to the right, what's going to happen? And this is nature, this is physics at work. What's going to happen if we're not directly over the center of gravity, the load's going to naturally find the center of gravity, and it's going to settle in a position below the hook. And when it does that, it's like you're going to have swinging movements, dynamic movements. You might have spinning. You are likely to have a load that's not level during the lift. But you don't always have to have a level load, as I've said before, but that is what we shoot for as a best practice in any kind of overhead lifting operation. If you're using multiple leg slings, which is quite common, really I recommend 90% of the time you need multiple leg slings. Most of the time a single leg like we have here, this is single up here. This is multiple down here. If you are using a multiple leg sling configuration, you want the center of gravity below the hook, but also contained within the rigging triangle or the sling angle that we have here. Another best practice, and this has to do with the vertical center of gravity or the vertical plane center of gravity. Ideally, the pick points will be above the vertical plane center of gravity. If the pick points are below the center of gravity, there's the risk of that load toppling over during the lift. You don't want that. You don't want that to happen. Now, if there is a type of load like we have here, like we have configured here in this diagram, if you have this type of load and you want your pick points below the center of gravity, that's what we have here. There is a way of doing that. Extra care needs to be taken, extra precautions needs to be taken to prevent the toppling from occurring. You can't have this type of configuration here, and this is an important point. This would not work with two sling legs. And we're just looking at the end of the load or the side view of the load, where it looks like there's only two sling legs. But you would want at least, in my opinion, 4 sling legs if you're handling a load on a lifting platform with a spreader beam. And this is a little more complex rigging configuration. We have our hook, we have slings connected to a spreader, then we have slings connected to a lifting platform that the load is sitting on. And these pick points here are below the load center of gravity. If done correctly, if done with care, it is safe. But if we're not careful and we connect to a pick point or pick points below the center of gravity, the whole thing could fall over, topple over in midair. It could topple over as you're lifting the load. You may not even get it into the air. depending on some different variables that may be at work in the situation. We've alluded to this, talked about this already, but here's another example. Let's say we have a load setting on a level supporting surface, and the hook is not positioned directly above the center of gravity. When this load is hoisted, when it breaks contact with the supporting surface, the load's going to go out of level. And if there's rapid hoisting, if they're trying to move the load at a rapid rate, if they're lifting it with a lot of velocity, that load's going to swing. It's going to swing as it settles into this level or out of level position. And swinging places increased stress on the rigging, on the crane, on every part of the lift is going to receive increased forces or dynamic loading in this type of situation. Another example of why rigging to the center of gravity is important. All right, knowing the load center of gravity is important for rigging design and lifting suspended loads. Like I've said before, it's really important for any type of material handling, including forklifts and even manual lifting where workers are picking up boxes or crates manually. Videos 2 and 3 will cover the quantitative methods for identifying the center of gravity of simple odd-shaped loads and also the center of gravity for more complex load systems, or what I call system loads. Video 4 is going to take a closer look at how center of gravity affects sling loading. We're also going to talk about pick point determination. All right, if you have any questions, let me know. You have my phone, you have my email, you have other ways of contacting me if you're an NSU student. So let me know if you have any questions. Videos 2 and 3, we're going to get more into this and the methods for identifying the center of gravity of a load.